All right, we're rolling. Okay, so this course is a basic introduction to mechanics of physics. So that includes things like Newton's laws, kinematics, energy, and momentum. Um, and it is a review class. So it is kind of assuming that you've taken some level of physics previously in high school, whether that was a regular level or an honors or AP. Some understanding of physics is helpful, although I will do my best to try to hit all of the really important topics. Um, and we're kind of assuming that if you're taking this class during the summer, that you, okay, Colby, thanks for letting me know. If you're taking this class during the summer, you are probably either trying to get a head start on college physics when you get there, or you just would like to make sure that you are as solid as possible. So I see a couple of you have not taken any physics before, and that's okay. I'm going to do my best to explain it as clearly as possible. Yes, it will be posted to Canvas later on, so you can go back and view it. It's not there yet, but I'll post it after this. IB Physics, awesome. Okay, well, if you have any questions, especially if you haven't taken physics before, please do let me know, and I'm happy to answer them for you. I would recommend that if you haven't taken physics before, that you go back and do some of the assignments that I post on Canvas that correspond to the material. Okay, cool. And that will really help kind of solidify these concepts. You'll see all of these again when you get to university physics. And I'm working alongside one of the Physics 1 instructors at FIT. So I'm pretty confident that the material that I am going over in this class will help prepare you for that class that you'll take in the fall, in the spring, that sort of thing. Okay, awesome. So meeting times and days, we are going to meet Monday, Tuesday, Wednesday, Thursday from 3 to about 4:30 on Zoom, and it will end on July 31st. There are no holidays that fall on those particular days, so you can expect to be here every day, Monday, Tuesday, Wednesday, Thursday. And Fridays, we will be having optional enrichment sessions. So those will look different week to week. Sometimes that might be having a guest speaker who's on faculty at FIT talking about the department or research that is being done at Florida Tech, or all kinds of various things that might be interesting to incoming freshmen. We have two sponsors who are helping us with this program. And you can see there, Collins Aerospace and Leonardo DRS are our two sponsors. So they have volunteered to take a session, I suppose. And some of that might include tips on how to be successful as you go to college, things like study skills and that sort of thing. Quick question for you guys. Can you see my group chat window in the video in my screen share? No. Okay, cool. Just checking. Awesome. All right, so our location is on Zoom, and my name is Laura Zamora. When the class was published, it was published under my maiden name, Laura Zagorski, and my email is also lzagorski 2010. I did my undergrad at FIT, so I have a really old FIT email, but I got married since then, so my last name no longer matches my email. If you forget and still call me like Mrs. Zagorski or whatever, that's fine. But my last name is actually Zamora, which is kind of cool because my name rhymes. Laura Zamora. I love it. And it's very convenient that I didn't have to change my initials when I got married. How long ago? I will get to that in just a minute. I have an About Me slide coming up, I think, next. But office hours, if you have questions about any of the assignments or questions that you want to ask kind of one-on-one instead of in this big group session, then you are welcome to just shoot me an email and I can schedule a time with you. I don't have set office hours, but I'm happy to jump on Zoom and meet up with you one-on-one if that is requested. Okay, so about me, I got married in 2013. So I was still in my undergrad at FIT. I just finished my junior year, which let me tell you, planning a wedding junior year of college is no joke. But we did it, we got married, and you can see in that top picture, that's my husband, Abraham. I have two adorable kids, not that I'm biased, but they're pretty adorable. AJ, my son, is 3, and Lily, my daughter, is 6 months old. I had her, thank you, I had her the week after final exams finished in the fall semester, December 18th. So that was a little bit of a stressful final exam period for me. But, oh, nice. Yeah, PhD in space science bucket list. Do it up. It's awesome. But yeah, I love my kids. They're great. And they may occasionally make guest appearances in this video because they just love to see what I'm doing. Okay, yeah, so I graduated from Florida Tech in 2014. I got my bachelor's in astronomy, astrophysics, and right now I'm working on my PhD in space science. I've had 1 full year of grad school, and I'm about to start my second. So if you have questions about grad school, I can give you a little bit of insight about that. I am working on my PhD at Florida Tech as well, yes. Yes. I taught physics, regular level and honors level at Melbourne High School, and I also taught honors astronomy there. Astronomy I only taught for 1 year, but physics I taught for 4. I love teaching. I'm a little bit of an awkward person. You might have gathered that a little bit at this point. But I just really enjoy teaching high schoolers because we're all kind of awkward people together, and it's great. So that was really fun, but then I decided to go back to school and start working on my PhD. So I am a GSA at Florida Tech, meaning I'm like a teaching assistant there. If you take Physics 1 lab, I may be your teacher for the lab class. So that's kind of cool. You'll see me around campus if you're going to Florida Tech in the fall. I love science, obviously. Physics cat memes, you'll see those appear periodically through my presentations. I love puns. I think they're the greatest thing ever. So if you have any great science puns, please share them. I love music. I play cello predominantly right now, but I've played a bunch of instruments in the past as well. Knitting. My husband calls me an old lady because I really like all of those knitting and embroidery and that sort of thing. Camping. My husband was a park ranger in Yosemite National Park before we got married, so camping is kind of the thing that we do together during the summers, hiking and that sort of thing. Legend of Zelda is one of my favorite video games. Doctor Who, I grew up watching that show, and it's just super science nerdy, so it's great. And I love the Bible. I think it's really fascinating. So those are kind of my current passions. Cool, transiting exoplanets. Nice. That sounds really awesome. Okay, so here's a brief outline of the class. The reference textbook that I'm going to be using is University Physics with Modern Physics by Young and Friedman. I have an old edition because it's from when I was an undergrad in 2010. I think the newest edition is the 15th. I have the 12th. So all of the example problems and book problems that I'll be posting correspond to my version, which is the 12th edition. So if you already have the textbook, if you're already in college, or if your college is going to require it in the fall and you're looking at a different edition, just beware of that my problems might look a little bit different than yours. But I'll be posting answers to the book problems as well, so that if you are looking at a different version than you're used to, you'll still have those answers. So you can see there kind of a basic schedule of what the class is going to look like. I did post these on our Canvas calendar as well, but these dates are subject to change depending on how comfortable you feel with the material. So if we need to spend a little bit more time in chapter 5, Newton's laws, that's fine. This schedule it can be flexible. And there are 2 days of review at the end of the course. So we have a little bit of wiggle room there if we need to extend some things. So you can see we'll be studying vectors, motion in 2 and 3 dimensions, so projectile motion as well. Newton's laws, which you might have some experience with even if you haven't taken physics officially. Some schools teach it in like middle school as well. Work and energy, momentum, collisions, rotational physics, and equilibrium. And there are a couple of additional topics that might appear in your Physics 1 class at a college level. But unfortunately, in a 6-week environment, we're already going to be moving through these kind of swiftly, so we can't get everything, of course. If there are some topics specifically that you're interested in, though, like I know seeing in the chat, a lot of you are going to be astrophysics or planetary science majors. So if you would like to incorporate some of those additional subjects, let me know, and I'm happy to work those in as well, gravitation, that sort of thing. So if you have a favorite physics topic that you want to go through, send me an email so that I can go back and look at it again later, because this chat will close once Zoom closes. So yeah, just let me know and I'll be happy to work it in as fast as we can. Okay, so about this class, it's a little bit different because there are no real grades for this class. This is a review course, so I will be posting assignments, but they are just kind of recommended problems that might be helpful for you. And I would advise you that the topics do build on each other. So take a look at some of the problems. Even if you don't do all of every assignment that I post, then that's fine. That's up to you, whatever you need to help you be successful. But I do recommend taking a look at least some of the problems for each chapter. Your participation in the class and your understanding of this are directly related to each other. So I know there are some students who actually aren't here right now because they are at work or some other thing like that. So if you're watching this on YouTube later, please know that you also can participate. You can send me questions and that sort of thing. And your effort that you put into this corresponds to the results that you will get out from this. I want you to have a conceptual understanding of this by the end of the course. So sometimes there are a specific set of steps for solving different types of problems, but it's more important for you to understand the concepts and how they relate to each other than to just memorize a series of steps. So I'll give you a kind of problem-solving guideline, and we will use it a lot. We won't use it every single time, but make sure that you understand how different variables relate to each other and how these concepts tie in and build off of each other. Physics is a math-heavy science, so it is kind of important for you to feel comfortable with some of these math courses, so trig, vectors, algebra, that sort of thing. I know a link for a pre-survey got sent out to all of you. If you haven't done it yet, please do so. I don't have the results in front of me right now for that. So if you could just really quickly take a second and type into the chat, maybe like on a scale of 1 to 5, how comfortable you feel with those types of math classes. 5 being super comfortable, and then 1 being you need some more review with those types of things. Okay. Great. Wow, that's awesome that your high school had that. Okay, and there's no shame. I would have said going into physics, I did not feel super confident with math, and that's okay. You know, we work through it, and I'm here to help you. So if you need a little bit of review, hopefully this class will help give you a little bit of review for those sorts of things. You seem very dedicated, so that's good. Dedication is going to help. So yeah, ask for help from me, of course, as your teacher, but also fellow students. So you can see in this chat here that some people feel super confident with their math abilities, some people less so. So if you have questions, help each other out. I know a lot of students can sometimes benefit from things like Khan Academy as well, online videos, that sort of thing. And of course, when you're asking for help, it's always better to ask early rather than late. So if you don't understand something in lesson 1 that we go through today, don't wait until week 5 to tell me that you don't understand. We are going to be doing calc-based physics. I say that tentatively because I don't want to intimidate you. Calculus is kind of like fancy algebra a little bit in my mind. So I would say it'll be predominantly algebra based for sure, and then I'll introduce some of those calculus concepts to you so that you aren't surprised by them when you see them at the college level. And I think this is a really great environment for you to learn those types of things because there are no formal grades. So this is your chance to kind of not experiment with it, but be introduced to it, I suppose. We might do some deriving of the formulas, but it kind of depends on the pace that we can go at. We'll definitely be doing some like introductory calculus starting later this week, things like derivatives, which is basically a fancy way to say taking the slope of a curve on a graph. So I would say that's more the kind of calculus that we would be doing. And as far as algebra goes, things like, you know, remembering your orders of operation when you're typing equations in, solving problems, that sort of thing. Knowing how to rearrange equations. So if I give you the equation F equals MA, how would you solve that for A? A equals what? That sort of thing. You'll definitely be able to learn derivatives. I have full confidence in you. They are some fancy, scary words, but don't be intimidated. You'll be fine. This picture just makes me laugh. Yes, I will be posting the slideshows as well. They'll be on Canvas. I'll post all of them on Canvas, and then so the slideshows are going to be on Canvas, but these videos are going to be on YouTube. I'll post a link to them on YouTube. Okay. Physics does tend to intimidate some people, but I don't think it should because you've been learning physics your whole life. You just might not have known the fancy words that people call these things. So my goal is to help you kind of look out into your experiences and into the world and universe around you and see all of the different ways that physics is the world around you. So yeah, don't be intimidated. Don't cry. You'll be fine. And I think it'll really open your eyes to see how complicated and yet ordered our world is. Good luck. You're going to do great. Okay, so here we go. We're going to officially launch in now. Chapter 1 is units, physical quantities, and vectors. Okay, so today we're going to be focused on units and conversions between these units. This is going to be kind of a math skills review. So you've probably seen this sort of thing in chemistry, if you took chemistry in high school. And definitely if you took physics in high school, this is something that you should have seen before. This quote underneath the heading is something that I took from Dr. Harris, who's teaching Physics 1 at FIT, because I just thought it was so funny. What time will it be in 3.5 kilograms? Obviously that makes no sense. So things like units are really important for us to understand. And Angry Physics Cat is not amused by bad conversion factors. So this is going to cover sections 1.2, 1.3, and 1.4 in the textbook. So if you have the textbook, feel free to follow along. If not, that's fine. Don't go buy it if you don't need it. Okay, so the book does suggest a problem-solving strategy that might be helpful as you go through some of these problems and examples. Most of the examples in the textbook do use this strategy, and I'm going to use this strategy as well. I might not say it explicitly every time, but this is kind of the general outline that they use for thinking through problems. So we're going to remember the acronym IC. The I stands for identify. So you want to figure out what the relevant concepts are in the problem that you're solving. And it's very important that you don't skip this step. Otherwise, you might forget what it is that you're trying to find halfway through the problem. And then you've just wasted all that time. So to identify, you're going to determine what the target variable is or what you're trying to find. And usually that's explicitly stated for you in the problem. That might tell you how fast is the car moving. So obviously you're looking for speed as your target variable. Or how long did it take the ball to reach the ground? Then your target variable is time. So it's important that you learn how to pull out that key information from the problem. S stands for setup. So you're going to set up the problem and try to pick out which equations would be helpful for solving that particular problem. I definitely recommend drawing a sketch of the scenario to kind of help you focus your thoughts and figure out what variables you've already been given and what it is that you're looking for. Especially as we go through vectors tomorrow, drawing a picture is going to be really helpful. The first E stands for execute, so that's actually going through and solving the problem. So make a list of all of the known and unknown quantities, and then actually doing the math. So solving the equations, getting that target variable, that's in your executing of the problem. And you're actually not done at that step, even though it seems like you should be. The last E is evaluating, and this is a really important step, asking yourself, does this answer even make sense? So make sure that you go back and check your units and your sign, whether it's positive or negative. So if, for example here, if you're solving for the radius of Earth and you get an answer of 6.38 centimeters, you might have done something wrong. Or if you get a negative radius, that doesn't really make sense either. So make sure that you take a second to look at the answer that you arrive at and ask yourself, does this actually make sense? Does this actually answer the problem that I have been given? Okay, so just want to give you like a real life example of why this is an important thing to do, units and conversion and all that sort of thing. The Mars Climate Orbiter was a spacecraft that was launched in 1999. How many of you were alive in 1999? Just give me like a yes or an I was. Okay. Woohoo! I was too. Okay. Cool. I feel you, Julia. It's a struggle. But anyway, even if you weren't alive in 1999, this spacecraft was for a while. NASA lost contact with it 9 months after it was launched. And so they were trying to figure out what happened. So this spacecraft was designed to investigate and map the evolution of the atmosphere and the climate and the surface of Mars, and then communicate with the Mars Polar Lander as well. But it missed its intended orbit, which was 87 to 93 miles above the surface. And it fell into the Martian atmosphere at 35 miles of altitude and then disintegrated. So that's kind of unfortunate because it was a $193 million project that just fell apart. So that was super unfortunate. And they were trying to figure out what was wrong, and what had happened was actually part of the scientists that were working on this project were using metric units, and part were using English units. And so some of the commands got sent to the Mars Climate Orbiter in English units as opposed to metric units, and those two things are not the same. And so it ended up breaking apart this orbiter, which is super unfortunate. I do kind of have a bucket list, and maybe I'll share some of that as we go a little bit. Going to Mars is actually not on my bucket list, but going to the moon is. So thinking about the Mars Climate Orbiter and things that we've learned from that, we should learn that units are very important. But also thinking about this idea of dimensions. So we're going to use this term in a couple of different senses. You might have heard like 2 dimensions or 3 dimensions as far as like spatial things go. But a dimension can also be defined in a different way. And here it is. A number gives us an amount. So like 2, 3, that gives us an amount. But an amount of what? And that what is called a dimension. So whether you're talking about 2 apples or 4 pears or whatever, that particular thing is called a dimension. So it has to be measurable, and it's measured in units. So there on the slide, you can see the common dimensions and units that we'll be using. The 3 big ones for us are going to be length, L, time, T, and mass, M. And so inside the parentheses there, you can see the units. The metric units are what we will be using in physics. That's kind of the standard for science. So the unit for length is meters. The unit for time is seconds. And the unit for mass is kilograms. Now you might see something a little bit confusing. The fact that length units are meters, which is a lowercase m, and mass, the variable, is also a lowercase m, usually. So it's going to be important that you pay attention to what context those things are in to see if you're referring to meters or mass. You can see crossed out, I have some other units. Those are the English units that you might be comfortable with. Inches or feet, things like pounds. We aren't going to be using those, but you might see those in some of the problems. If you see those units in the problems, you'll have to convert them into your metric units. And I'll go through step by step how to do that in just a couple of minutes. An important thing for you to keep in mind is that in math, variables can pretty much mean whatever you want. So whether you're talking about X, Y, Z, A, B, C, if there's some unknown something, you can just call it a letter, and it doesn't matter which letter you choose, you just solve the problem with that particular letter. But in physics, that's not the case. You can't just pick whatever letter you want. They're fixed. So capital A stands for amplitude, whereas lowercase a stands for acceleration. And capital V stands for voltage, whereas lowercase v is velocity. So each letter, and Greek letters often as well, refer to a particular thing. Each one of those has their own units as well. Most of the other units that we'll be referring to throughout the class are some combination of those three base units that you see on the slide. For example, speed is going to be meters over seconds. Newtons is kilogram meters per second squared. So some combination of these things is also very common to see. Okay, so when we're using these dimensions in equations, it's really important that you have consistency in your dimensions and your units. So that quote that I had at the beginning, what time will it be in 3.5 kilograms? That doesn't make any sense because you don't measure time in kilograms, you measure time in seconds. So that's an inconsistency that would cause you a lot of problems if you were trying to solve a problem that way. Same thing as this brick is 17 seconds heavier than that rock. Well, that doesn't make any sense either. So it's important that we use the proper units for the quantities that we are referring to. And there are some rules when we're dealing with dimensions and units. When we're multiplying or dividing quantities, the dimensions don't have to be consistent. But when we're adding, subtracting, or claiming equality, they do have to be consistent. So for example, meters per second, meters over seconds is totally valid. But saying 5 seconds equals 2 seconds plus 3 seconds, that's fine. 5 seconds equals 2 seconds plus 3 kilograms, that's not okay. We can't do that because those units aren't the same. There's no consistency there. Okay, exponents must be dimensionless, so you can have 7 to the 3rd power just fine, but you can't have 7 to the 3 kilograms power. That doesn't really make sense. Trig functions, we will be dealing with those pretty frequently as well. Trig functions, the arguments of those must be an angle, and those are going to be in degrees or radians. I prefer to think in degrees. Some of you might prefer to think in radians. And there are times where one will work better than the other. But either way, when you're dealing with the trig function, you can't have the sine of 3 kilograms. It has to be the sine of 30 degrees. And numbers are dimensionless just by themselves. 2. That doesn't need to have a unit with it unless you're referring to a specific quantity. Okay, so when you see that picture of the cat in the corner, it's a problem that I want you to try yourself. So I'm going to give you a couple of minutes to think through this example. So I want you to figure out which expressions or equations are valid based on their dimensions or their units. So they need to have, remember, consistent units. 5 seconds equals 2 seconds plus 3 seconds. That's fine. So take a couple of minutes, look through those expressions. I gave you down at the bottom what the variables mean and what units they're measured in. So x is distance, which is in meters. V is velocity, which is meters per second. T is time, which you measure in seconds. And A is acceleration, which we measure in meters per second squared. So if you have paper handy and you want to write it out, that's fine. But I'm going to give you a few minutes, like I said, to just think through those and see if you can figure out which ones are good expressions and which ones are not. We'll take another minute or so, and then I will go through all the answers all together. So if you're stumped a little bit, don't worry, I'll explain in just a moment. You're not dumb if you don't know how to do this. It's totally fine. This is kind of a way to check what you already are comfortable with, and if that's not this, then that's fine. We'll go through it. No worries. I will never think you're dumb. Okay, great. So I'm seeing some responses from some of you, and that's good. You don't have to share your responses if you don't want to. Um, but let's go through and see. All right, so A, B, and E are all valid expressions based on their units. So for A, X was measured in meters. Sorry, I don't have that on this slide as well. But X was measured in meters, and V, velocity, is measured in meters per second. T is time, measured in seconds. So when we have meters over seconds times seconds, the seconds on top and bottom cancel each other out, and we're left with meters plus meters as our units, which is totally fine to do. B, velocity, is in meters per second, minus 2, that doesn't have any units with it, it's just a number. X is meters, T is seconds, so we have meters per second minus meters per second. That's totally valid. When we look at C, C, mass, is measured in kilograms, and 4 is just a number. It doesn't have a unit with it. So that doesn't really make sense to have kilograms plus a number. Those units they don't match. You could have 4 times m, but you can't have m plus 4. Emily, did that answer your question? Okay, great. So looking at D then, 5 times A is meters per second squared, equals 3 halves V. V is meters per second. Those numbers don't have units associated with them. So we're just looking at A and V, really. And meters per second squared is not the same thing as meters per second. So those two are not consistent in their units. And then the last one, X, is meters. We already know that V times T cancels out to be meters as well from part A. And then looking at the 1/2 AT squared, T squared is a time squared, so seconds squared. Acceleration is meters over seconds squared. So when we have the seconds squared on top and the seconds squared on bottom, they cancel each other out, and we're left with meters equals meters plus meters, which is totally valid to do. If you need a little bit more practice thinking through those, I can post some additional problems on Canvas for you to look through. The back of the chapter in the textbook has some great ones, so I'm happy to post some practice ones for those as well. Okay, scientific notation. Why do we use scientific notation? Well, it's really convenient for making really big or really small numbers a lot easier to handle. And in physics, we often have really big and really small numbers. So I have a space example because I'm a space nerd. What's the average distance between the sun and the earth? 93 million miles, or 9.3 times 10 to the 7 miles. When you are typing in distances like that into your calculator, it's much, much easier to type them in scientific notation other than typing out all of those zeros, especially for the next example. What is the charge of an electron? If I had to type all that in my calculator every single time, I would just bang my head on the desk, I think, because that's just too many zeros to try to keep track of. It's a lot easier for me to think about 1.602 times 10 to the negative 19. Yes, 6E7, that E means the same thing, you're right. And that's totally valid to do. So scientific notation is very, very helpful, and I recommend that that you use it as often as necessary. It's not always necessary to put your answer in scientific notation. Like if you get a speed of 43 meters per second, you don't have to put that in scientific notation. But for your own sanity, I do recommend putting really big and really small numbers like those into scientific notation. I have some practice problems that go through that as well. But here's how to write a number in scientific notation. I know it's summer, it might have been a while since you've seen this. So to write a number in scientific notation, we put a decimal point after the first non-zero digit, and then we drop the following zeros. So when we're dealing with 93 million miles, sorry, that should be 93 comma, not 93 dot. I'll fix that when I post this. But we put a decimal point after the 9 to turn into 9.3, and then we can drop all of those following zeros. Then we multiply that coefficient, 9.3, by 10, and then to find the exponent, we just count the number of places from the decimal to the end of the number. So we moved the decimal place over to the left 7 places to get it behind the 9. So our exponent is 7. Okay. So when you think through writing your numbers in scientific notation, you do have to be careful to not just count the zeros, because 93 million has 6 zeros. But the exponent is actually 7 because we have to move the decimal place all the way over to behind the 9, not behind 93. To have a proper scientific notation, the decimal, well, the coefficient has to be a number between 1 and 9.999. No, repeating. So we need to move the decimal place over to the first, behind the first non-zero digit. So another tip that I would recommend trying to remember is if the original number is bigger than 1, your exponent is positive. And if it's smaller than 1, your exponent is negative. Positive exponents deal with really, really large numbers, and negative exponents deal with small numbers. Okay. So here's another, give it a try. If you have scrap paper, great, it might help to write these down. But here are a couple of numbers, and I want you to try to put them into scientific notation. So here's the first one, 235,000. How do you write that in proper scientific notation? Take a second. Comma here does not mean decimal. I'm seeing some answers. Good, good. I will say that some of the answers have been correct and some have not. I'm also seeing several different formats for your answers, which is interesting and totally fine. So our correct answer for this one I know you've all been waiting on the edge of your seat, is 2.35 times 10 to the fifth power. And it's to the fifth power because when we see a whole number like that, the decimal point is kind of assumed to be at the end of it. So this would be the same thing as saying 235,000.0. So the decimal place is just kind of assumed to be at the end there. Remember, the coefficient that goes before the times 10 in our scientific notation must be a number between 1 and 9.99999. So we put the decimal place, we move it over until it's behind the first non-zero digit. So we need to move the decimal place all the way over until it's behind the 2. So I usually use like my finger or a pencil and physically move it across the number. So I start at the end of the number and I go 1, 2, 3. Now I'm past the zeros at the comma. And then we still have to get past the 5 and past the 3 to get our decimal place where it needs to go behind the 2. So in doing that, we've moved the decimal place over 5 places in our number. And so our exponent in that is 5. And yeah, I did see a question in the chat. You don't understand what the E is. That's a different way to write times 10 to the something. And I'll actually go through that in one of the slides in just a minute. But it's basically shorthand. It means the number following the E is the exponent in your scientific notation, E for exponent. And it means the exact same thing. It's just kind of a shorthand way to write it. Yeah, which thank you for those of you who answered that question in the chat. E is so much cooler than E. Yeah, E's. Oh, okay. So here's another one. And if you look really fast, you might have seen the answer. But go ahead and try to put this one into scientific notation as well. Good, I'm seeing some answers, and I like the answers that I'm seeing. That's awesome. Yeah, so our correct answer is 1 or 1.0 or 1.00 times 10 to the negative 4. Some of your professors might care about sig figs, significant figures. I don't care for the purpose of this class because this is just to review the concepts. So all of those answers that I see in the chat, whether it's 1 or 1.0 or 1.00, those are all totally fine with me. Yeah, a good rule of thumb is 3 sig figs. That's kind of the standard. And there are actually real sig fig rules to determine how many you need. Since it doesn't really matter for this class, I didn't include them, but I'm happy to go through that later on if you guys want a refresher on determining the number of significant figures to include. Okay, so here's the next one. Try this one. What is this in scientific notation? Good, yeah. I'm seeing great answers from everybody who's posted an answer. So 5 times 10 to the third is our correct answer because we took that decimal place from the end of the number and we moved it over 3 places to put it behind the 5. And so our exponent is 3. And it's positive 3 because we moved it to the left. Our number is bigger than 1. Okay, I think this is the last one that I want you to try. Great, great, good. All good answers. Yeah, exponent -2 because we moved our decimal place to the right 2 places to put it behind the 7. Good. Okay. So if we have a number in scientific notation and we want to convert it back to standard notation, we just do the opposite thing of what you just did to put it into scientific notation. So if our exponent is positive, we move the decimal back to the right to make that coefficient number larger. And if the exponent is negative, we move the decimal to the left to make the coefficient smaller. But in either case, you move the decimal the same number of places that matches the exponent. So the speed of light, 3 times 10 to the 8 meters per second, or written out in standard notation, 300 million meters per second. Gravitational constant, 6.67 times 10 to the negative 11 would look like that. And remember, there are not 11 zeros after the decimal place. There's 10 zeros after the decimal place because you would have to, include the 6, that first 6, as one of your places that you move it over. Okay. So I want you to pull out your calculator and your phone if you have those things handy. There are a couple of shortcut buttons that will make your life a lot easier. And I want you to actually find them on your phone and on your calculator right now so that you know how to use them when you're working on practice problems and things like this. So go ahead and pull out, I know I'm telling you to pull out your phone during class. But yes, please pull out your phones. I don't actually have my calculator on hand, but I do have my phone, which is why I'm teaching you on both, because you'll probably always have your phone, but you might not always have a calculator with you. So there are, I know, TI-84. I still have mine from high school. It has a Spider-Man sticker on it. It's great. There are a couple of shortcut buttons that I want you to look for depending on which calculator you have. And if you don't have a calculator that matches any of these, then that's fine. Just look at what you have, of course. So to type it into your calculator, you would type the coefficient, the value that comes before the times 10 to the something. And then instead of physically typing the times 10 little caret symbol, instead of hitting all of those buttons, you probably have a shortcut button on your calculator. So one of the shortcut buttons would be EE, or you might have an actual times 10 to the X button or an EXP button. So this is the app that I have. I put it on my a picture of it in the PowerPoint too. This is not the one that came on my phone. I downloaded a specific scientific calculator app, but mine has the EXP button, and that's my scientific notation shortcut. Keep in mind, on your calculator, I also have the TI-84, and that EE is kind of hidden on top of that comma button. So that means that you have to hit the second comma, and then that will get you to your shortcut. If you have an iPhone and you have a scientific calculator, you turn your phone sideways, it'll pop up with the scientific calculator. You have your EE button. Please keep in mind, little e is not the same thing as capital E, capital E. And unfortunately, the iPhone app has them right next to each other. We want the 2 capital E's, not the lowercase e. That is something totally different. So you would type in your coefficient, press one of the shortcut buttons, hit equals or enter. I'm sorry, type your exponent and then hit equals or enter. And then that's your scientific notation. The answer that it gives you might be formatted as 9.3e7, which is the same thing as 9.3 times 10 to the 7, like we already talked about. And that number after the e tells you what your exponent is. Okay. So in the chat, just give me a yes or no if you were able to find the shortcut button on your calculator and your phone. Yeses, yeses. Good. Awesome. Yes. Great. Okay, so give it a try. We're going to use our calculator, solve this problem. So I want you to type in those numbers, scientific notation, into your calculator and get your final answer. 2.34 times 10 to the 5th times 1.89 times 10 to the 7th. Could I send a link? I will post some resources on our Canvas page that could be helpful to you. I can't send them right now, of course, but I'll post them after this class. Good, I'm seeing some answers. So this is what I got, 4.42 E12, or 4.42 times 10 to the 12th. They mean the same thing. And it looks like that's what most of you got as well. I rounded mine to 3 sig figs. Some of you left it in 4 sig figs. For me, that's fine. Okay, great. If you don't have a calculator, yes, you can still math with scientific notation. It just takes a little bit more work. So if you have like a normal calculator, not a scientific calculator, when you're adding numbers in scientific notation, make sure everything is in the same power of 10, and then you add the coefficients. So here we have 4.215 times 10 to the negative 2 plus 3.2 times 10 to the negative 4. We can put that into the same power of 10 by moving our decimal place over 2 places to get 0.032 times 10 to the negative 2, and then you just add the coefficients. Can you hear me better now, Alessandro? I hope so. I'll try to speak up. Okay, to subtract, you basically do the same thing, except you then subtract your coefficients. So get it to the same power of 10, subtract your coefficients, there you go. If you're multiplying the numbers, first you multiply the coefficients, and then you add the exponents. So 3.4 times 10 to the 6 times 4.2 times 10 to the 3rd, you take out those the coefficients and multiply them, 3.4 times 4.2. And then you add the exponents on, so times 10 to the 6 plus 3. When you're dividing, same idea, you divide the coefficients and then you subtract the exponents. And when you're raising to a power of an exponent, you raise the coefficients to the power, and then you multiply those exponents together, and that will give you your final answer. So if you ever stuck like on a test or something without a scientific calculator, you can still do the problems if you follow those rules. Okay. So metric prefixes, metric powers of 10. You probably have seen these before, especially if you took physics in high school. But even if you took chemistry or something, you've probably seen a table like this before. So we can, when we're dealing with, excuse me, when we're dealing with really big or really small numbers, we can use scientific notation to help us, but we can also just adjust the units that we're using. That's called converting our units. So the left-hand column of our table is the multiplication factor. That tells you how much bigger or how much smaller that particular prefix is than your base unit, than 1 of like 1 meter, for example. And that corresponds to a power of 10, or a scientific notation exponent. The symbol that you see will be written before your base unit. So, for example, if we're dealing with meters, like really small increments of length, we might use centimeters, cm. If they're even smaller lengths, you might use millimeters, mm. And so that symbol comes before the unit, and then the prefix is what we would say before the unit. So centimeters, or millimeters, or kilometers, kilometers. So this is just a way that we can adjust the units that we are using. Megaparsecs is beyond the scope of this table. That's like the biggest distances that we could possibly come up with, which of course you need for astronomy. So the 3 that are in the table with the stars next to it, kilo, centi, and milli, those are going to be the most commonly used ones for this part of physics. You will use the other ones in other parts of physics, but for this class, those 3 are the ones that I really want you to know and be comfortable with. It might help if you, I also really like languages and words. It might help you remember these things if you think of other words that have a similar prefix. So let's think about years, for example. So 1 year is 1/10 of a decade, deci, and 1/100th of a century, and 1,000th of a millennium. So those words, decade, century, millennium, they all have the same sort of prefix as deci, centi, and milli. And so that might help keep them straight in your head. It does for me, at least. For the big ones, tera, giga, mega, kilo, you guys are at an advantage, I think, because you guys are so technological as a generation. So just think of storage, right? A megabyte is more storage than a kilobyte. And a terabyte is the most storage, I guess, as far as this chart goes. So you can kind of keep them in order in your mind that way. Giga Drain from Pokemon. Nice example. Okay, so when we're converting between units, if we're going from like an English unit to a metric unit, so inches to meters, I will give you those, they're called conversion factors. So for example, 1 inch is 2.54 centimeters. I'll give you those because they're kind of random a little bit. But you should know how to go from one metric unit to another. So how to go from meters, our base unit, 1 or 10 to the 0, how to go from meters to kilometers. 1 kilometer is 1,000 meters. So try to keep these metric ones in the back of your mind and know that I'll give you English conversion factors. So when we are converting between units, I like to set them up as ratios. I think that helps kind of visualize things. So we can say 1 minute is 60 seconds. That means they represent the same time interval. So if we set that up as a ratio, that means 1 minute over 60 seconds is 1. It's basically like saying 2 over 2 is 1. The same thing applies if you flip the ratio. 60 seconds divided by 1 minute is also 1 because 2 over 2 is 1, just like 2 over 2 is 1. So we can cancel out units when they appear on the top and the bottom of a fraction. And so when we're trying to go from one unit to another unit, we want to choose the ratio that allows us to cancel out units we don't want in our final answer. I have an example that I'll show you of this in just a moment. So whether we choose 1 minute over 60 seconds or 60 seconds over 1 minute depends on what we want as our final answer. And then you would multiply the numbers on the tops of the fractions and divide by the numbers in the bottom of the fractions. So here are some examples. How many hertz, Hz means hertz, are in 3,250 gigahertz? Well, giga means 10 to the 9. So we would start by writing out the number that we're given, 3,250 gigahertz. We write times and we set up our ratio. Okay, 1 gigahertz is 10 to the 9 hertz. And the reason why I wrote the ratio this way, with gigahertz on bottom and hertz on top, is so that the gigahertz units will cancel each other out. Right? Because this first number, the 3,250 gigahertz, is basically, there's like an assumed over 1 in that fraction. So gigahertz is on top in that fraction. And if I don't want it in my final answer, because I want my final answer in hertz, then I write gigahertz on the bottom of the next ratio. And they're on top and on bottom, so it will cancel out, and we're left with just hertz. So our answer there is 3.25 times 10 to the 12 hertz. I would take 3,250 times 10 to the 9, and we get that final answer. Okay. Here's another example. How many kilometers are in 225 millimeters? Well, we're given 225 millimeters, and that's our first number, first ratio, times, and here's where those prefixes come in handy. Milli means times 10 to the negative 3 meters. But we don't want our final answer to be in meters, we want kilometers. So we keep in mind that there's 10 to the 3 meters then in 1 kilometer. And again, the reason I have the ratio set up like this is so the units on top and bottom cancel out. Millimeters on top cancels millimeters on bottom. Meters on top cancels meters on bottom, and we're left with just kilometers, which is what we want as our final answer. Or you could write it this way, remembering that there's 1,000 millimeters in 1 meter and 1,000 meters in 1 kilometer. It's the same thing. You end up with the same answer, 2.25 times 10 to the negative 4 kilometers. Okay, any questions about those two examples? Great. I do have some example problems posted that will go through some of these, not example problem, practice problems that will go through some of these. They're already posted on Canvas for you, so you can go ahead and practice some of those as well. But we're going to do a couple more. I know we're running short on time now. But we'll go through a couple more because some of these are actually a little bit trickier than they seem. So thinking about how many square centimeters are in 400 square meters, when we have squared or cubed units, or to any other power really, we have to square or cube our conversion factors as well. So we start out here with 400 meters squared because that's what we're given. And here is our ratio for meters and centimeters. Okay, we know that 1 centimeter is 10 to the negative 2 meters. But we don't want meters, we have squared meters. So we square the top and bottom of that ratio. And so it ends up looking like this, 400 meters squared times 1 square centimeter over 10 to the negative 4 meters squared. We distribute that exponent to both the times 10 to the negative 2 and to the meters. So those units will now cancel out. We're left with square centimeters as the unit that we want. And there's our final answer, 4 times 10 to the 6 square centimeters. With these practice problems that I post on Canvas. You do not need to submit them. They are just for you if you feel like you need extra practice on these ideas. Okay, so when we convert between English and metric units, it's the same process, but the conversion factors are a little bit weird. We can't just look at the prefix in this case. So like I said, I'll give you all of these conversion factors. 1 inch is 2.54 centimeters, 1 kilogram is 2.2 pounds, 1 mile is 1.6 kilometers. I would give you those things in a problem because they're a little bit harder to remember all of them. But still, we would need to have consistent units in our final answer and in our equation. So here's an example converting between English and metric. How fast are you going in miles per hour if you're going 31.3 meters per second? Well, we're starting with a number that we're given, 31.3 meters over 1 second. And for this example, I'm choosing to get my time units correct first and then my distance units. But you can do it either way. So we know that there are 60 seconds in 1 minute. And since seconds is in the bottom of our first fraction, I'm going to write it in the top of our second fraction. But we don't want minutes in our final answer. We want hours in our final answer. So we're going to do another ratio. 60 minutes is 1 hour. And that way it allows us to cancel out the minutes and we're left with hours in the denominator, which is what we want. Now let's deal with the distance, getting meters to miles. Okay, so we know there's 1,000 meters in 1 kilometer. Meters cancels out. There's 1.6 kilometers in 1 mile. Kilometers cancel out. We're left with miles over hours, which is what we want. So our final answer is 70.4 miles per hour. Okay, so I want you to give this one a try real quick. The distance from Earth to the Sun is approximately 93 million miles. If 1 mile is 1.6 kilometers and 1 inch is 2.54 centimeters, how many inches away is the Sun? Write your answer in scientific notation. Take a minute and convert those units. All right, I'm starting to see some answers coming in, so I'm going to go ahead and start walking through the problem. But keep working if you're working. So this is how I would set up the ratios. We're starting with the number that we're given, 93 million miles. And we know we want to get to inches. Okay, so we need to get miles out of our final answer. We need to write our ratios so that miles on top cancels out miles on bottom. So our ratio is going to be 1.6 kilometers over 1 mile, so that miles will cancel out. Our next ratio is going from kilometers to meters. So 1,000 meters in 1 kilometer. That way kilometers on top and bottom cancel out. The next ratio is 100 centimeters are in 1 meter. So meters on top and bottom cancel out. And lastly, 1 inch is 2.54 centimeters. So centimeters on top and bottom cancel out. You can see all our units have canceled then, except for inches, which is what we want our final answer in. And so you can see there is our final answer, 5.86 times 10 to the 12 inches. So we got 93 million times 1.6 times 1,000 times 100 divided by 2.54. And that gave us our final answer. I know it can be really annoying sometimes and tedious to write your units out with all of these steps, but I definitely recommend that you do so that you can actually see how those units are canceling out and you don't get confused as to what's happening halfway through the problem. Okay, another example for you to try. The world's largest cut diamond is the first star of Africa, mounted in the British Royal Scepter and kept in the Tower of London. Its volume is 1.84 cubic inches. What is its volume in cubic centimeters? How about in cubic meters? So go ahead and think through this problem. Remember, 1 inch is 2.54 centimeters. And be careful because we're dealing with cubic units this time. So how does that change our problem? Go ahead and think through it. All right, I'm seeing some answers. So we're going to go ahead and start walking through the first part of the problem. All right, so we're starting with what we're given, 1.84 cubic inches. And so now we're going to start writing out our ratio. So we know our ratio, 2.54 centimeters is 1 inch. And again, I wrote it that way with centimeters on top and inches on bottom so that the inches will cancel out. But since our original unit is cubic inches, that means we have to write our ratio cubed. So that when we distribute that cubed exponent into our parentheses on both top and bottom, our bottom units become cubed. So we distribute that cube to everything inside the parentheses. 2.54 cubed, centimeters cubed over inches cubed. That gets rid of our cubic inches. Now our only unit is cubic centimeters. And there you have our answer. 2.54 cubed gives us 30.2 centimeters cubed. Okay. For the sake of time, because I know we're almost out of it, we just have a couple of minutes left, I'll go ahead and show you our final answer for cubic meters as well. And hopefully you are on your way to getting there. So I'm starting here at 30.2 cubic centimeters because it's a lot easier to start there as opposed to from the beginning again. So 30.2 cubic centimeters, we know there's 10 to the negative 2 meters in 1 centimeter. And again, we need to cube that ratio to get rid of our cubic centimeters. So we distribute that cube to everything inside the parentheses. That cancels out our cubic centimeters. We're left with cubic meters. 10 to the negative 2 cubed times 30.2 is 30.2 times 10 to the negative 6. Or, in actual scientific notation, 3.02 times 10 to the negative 5 meters cubed. If you feel terrible at this, you are not alone at all. This is I think it's kind of an abstract concept, and I definitely have practice problems available for you on Canvas. I will be posting the answers to the practice problems as well. I'll post them on Friday to give you some time to work through them. It's okay that you're not sending answers. I mean, it's also okay to send answers and be wrong. I'm not going to think any less of you. And I applaud you for trying. Even if you don't send answers, that's fine, but I applaud you for trying. Harder than calculus. It can be. It depends on how your brain works. I am confusion. Oh no. Well, when this video is posted on YouTube, you can go back and rewatch some of this. We do got this. We're going to be great. What tab in Canvas are the questions going to be in? They're going to be under Files. So if you go to our Canvas class page, you'll see a bunch of tabs along the side if you haven't been there yet. So you'll click on the Files link, and then you'll see some practice things there. The one that I have for this particular lesson is labeled O1 for Chapter 1, Units and Conversion Practice. Metric protest group. Lol. This was the main thing you learned in chemistry. Yeah, chemistry is pretty good to help with this. Okay. We're almost done. I have this bonus problem for you to take a look at. And I do want you to give it a try before class tomorrow. I'll be posting the answer as the very first slide that we go through tomorrow. Find the mass of an asteroid which has a radius of 3.5 kilometers and express the mass in terms of cruise ships. So there are some conversion factors that you might find helpful for this particular problem. And then there on the right side, I have how to get to that practice worksheet that I have for you. Okay, so give this problem a try. Even if you get the wrong answer, that's fine. Give it a try. The more you practice this, the better you'll get at it. And especially if you don't like doing this, that means that you should practice it, because this is a skill that we're going to be using a lot in the next 6 weeks. So it's really important that you feel comfortable with this. You don't have to send me the answer through Canvas. I will be showing you, like, we'll appear at this slide again first thing tomorrow, and I'll have the answer posted there so you can check your answer. Okay, so to just finish off, do you guys have any questions other than metric protest group and wanting more practice at this? Can we run this from the top tomorrow? Unfortunately, no, but you can run this from the top on your own time when I post this video to YouTube. Protest group meets at 4 on Fridays. That's fine. That's not my time. I will be posting to YouTube today as soon as I um, compile the video. Yes, we can go back to the question. All right. Well, if you have not already seen so, on Canvas there is a pre-test that I would love for you to do. And I say I would love for you to do it. It's actually a requirement, so I would love for you to do this required pre-test. It does not affect your grade at all because there are no grades. So just do your best. Answer whatever you think to be the correct answer. Of course, I don't know why you would do any differently on a test. But answer whatever you think is correct. And that will help me gauge what your prior knowledge is and the types of topics that you feel comfortable with and ones that you don't feel as comfortable with. So it's really mostly to just help me figure out where you're at right now. So if you go on our Canvas page, then you will look under either assignments or quizzes. You'll see it, it's called pre-test. It's a multiple choice test. So go through and take it. It will be graded automatically, but you will not see your grade at the end of it because it's just for me to diagnose things, diagnostic test. So please take it by Friday. I think the deadline is set at Friday, 11:59 p.m. So yes, go ahead and take that when you have a couple of minutes to do so. It doesn't have to be right now, but by Friday at 11:59 p.m. All right, it says some of you have already taken it. That's great. Go you. I don't know if I can save this recording in Canvas because Canvas has a limited storage space, but I will post a link to it on Canvas, and I'll see what I can do, I suppose. Okay. Well, if you guys don't have any more questions, then you are welcome to head out, and I will see you tomorrow at 3. I'll stay on here for a little bit. I'll stop recording, but I'll stay on here for a little bit if you have any questions.